Good afternoon and welcome you all for today's discussion. Today we are starting a new topic, that is a fluid mechanics, and in very first lecture we are going to discuss about fluid properties and how we define fluid, what is difference between fluid and solid, and we discuss what is a Newtonian fluid, what is a viscosity. So here today we are going to discuss about fluid properties, means what fluid is, how fluid can define, why how fluid can be defined, how it is different from the solids, and why it is very important, because you know that everywhere in our body, every your surrounding, atmospheric and all phenomena, you can see application of fluid, whether it is ship in sea or boats in sea or spaceship or aeroplane, aeronautics, astronautics, and everywhere, whether it is a lungs and heart and the blood flowing through our veins, everywhere there is a fluid. So there is a wide scale application, wide scale interdisciplinary application of fluids in every aspect of engineering, whether it is a metallurgical engineering or biomedical engineering or chemical engineering, everywhere, whether it is computer engineering, computer science, agriculture engineering, everywhere. Without fluid, nothing can be visualized. So fluid mechanics is one of the most important subject, one of the most important science and engineering subject of mechanical engineering, and it is applicable in every engineering, whether any interdisciplinary engineering or interdisciplinary relationship with fluid mechanics, with any kind of engineering. It is a very wide scale, whether spaceship Dragon taking astronauts from spaceship to the Earth, back to the Earth. You see that how when Dragon capsule enters into atmosphere, there is a huge temperature rise, and this is because of the interaction of fluid with the surface of the Dragon capsule. Due to this frictional resistance, due to viscous resistance of the fluid, there is a large increase in temperature. So it is very important to study fluid behavior, how fluid behaves fluid behaves in kinematic and dynamic action. So wide range of application. Starting, we will discuss main topics that needs discussion in class. So today we start from the one of the most important property of the fluid, that is a viscosity, coefficient of viscosity of fluid. So starting from the coefficient of viscosity, what is viscosity? Why viscosity arises? Viscosity, defined by dynamic viscosity, it is a mu. It is a dynamic viscosity. Wow, how we can define it? It is a fluid property. When there is a real fluid, for ideal fluid, there is a no viscosity. These are known as inviscid fluid, but real fluid always has viscosity. So viscosity, we know that fluid is made of the fluid. You see that there is a fluid, and this is a fluid inside the container, and you can see there are molecules, and there are so many molecules inside the fluid container. These molecules continuously interact with one another. They collide continuously with one another, and due to this collision and intermolecular forces acting between two molecules, and continuously these collides, and there is intermolecular forces also apply between two fluid particles. So due to these combined action of intermolecular forces and collision of molecule, property of resistance will create, and due to this resistance is known as a viscosity, and this is a property of the fluid by virtue of which there is a resistance between two adjacent layers. When we try to move upper layer of the fluid, then lower layer just adjacent, just in vicinity of the upper layer will resist motion of the upper layer. This nature of resistance is due to viscosity. That is a coefficient, that is a viscosity, is that property by virtue of which two adjacent layer of the fluid will resist. Upper layer will resisted by just lower layer, and just lower layer will be resisted by just below lower layer. So this continuously will occur, and the fluid that is in contact with the surface, due to condition of separation, condition of no separation, has velocity 0. So you see that in upper layer velocity will continuously increase. So here we see that how a fluid will behave differently compared to solid. When we apply force, why we try to when we try to twist the solid material, then after certain quantity of the twisting, certain quantity of the strain, it will stop further twisting when you apply torque. But when we apply torque or shear force on the fluid, it will continuously deform. It will whatsoever magnitude of the shearing force or torque, fluid will continuously deform, and rate of deformation is proportional to stresses that develop inside the fluid. Means when you apply stress or force on the fluid, it will start continuously deformation and reaches at equilibrium with constant rate of the deformation. Not deformation will stop. Deformation will not stop, but it is always proportional to magnitude of the stress that is applied to deform the fluid. Means the fluid will continuously deform under applied shear force, or simple we can say force. When we apply force, it continuously deforms and reaches at the equilibrium rate of deformation. This is a difference between solid and fluid. Solid will not continuously deform. It will stop deformation at the equilibrium position. Further we apply stress, it will break down, but it will not continuously deform. Continuously deformation is not possible for the solid, but continuously deformation is occur for the fluid. That is difference between solid and fluid. And fluid can be defined by two type of matter. It is either gas or liquid. Both are fluid. So here in fluid mechanics, mainly we focus on the liquid, that is a fluid. We will focus liquid, not gas. Either, but both are fluid. Fluid means liquid and gas. But in fluid mechanics, we are going to discuss properties of the fluid, and that one of the most important property, that is the viscosity, that we are going to define viscosity. Already we have defined what is this viscosity property, how it arises. Now we define what is Newton's law of viscosity, how we define fluid by Newton's law of viscosity, and how when we apply force on the surface of fluid, how it behaves. That I want to define by deriving Newton's law of viscosity. So let us see. This is a solid surface. This is a solid surface over which fluid is flowing, and here we take another body that is moving with velocity v. This is moving with velocity v naught. There is a liquid. There is a liquid, and it is a continuum. Liquid is under continuum, means there is no any separation between fluid. Means there is no continuum fluid is there between. This is a moving surface. This is a moving plate. This is a fixed place. So we know that under the condition of no separation, real fluid always follow the condition of no separation. When moving fluid come in contact with a solid surface, its velocity becomes zero at this point. At this point, everywhere on this point, velocity is zero. And as we move upward, y direction, velocity will increase. This velocity will increase. So let us see how we can define velocity distribution. What is the velocity distribution? Here velocity is maximum, that is v naught. As we coming deeper and deeper, velocity will continuously decrease. Velocity will continue. This is a velocity distribution between two plates. One is a fixed plate and another one is a moving plate. Moving upward, here velocity becomes zero, and upper velocity just fluid in contact with this moving surface of the plate. Velocity is v naught, and we go down, velocity is continuously decreasing. So velocity is a function of vertical distance. Velocity is a function of y. Velocity is a function of y. So here we define how we can derive velocity relationship between velocity and y. Means how velocity related to y distance. So let us see here 2 points. Suppose here at this point it is distance, here distance y, and velocity at this point is vx. Here velocity at this point is vx, and we move upward in y direction. That is this is point P and this is point Q. Here velocity becomes distance of this is del y. Del y is distance between these 2 points P and Q. Del y is distance between these point P and Q. So now after del t time, point will reach from here to here. And what will be velocity at this point? Here velocity will be equal to, because we know that velocity is increasing continuously as we move upward, and here velocity is maximum. So what is velocity at this point at Q? This velocity will be equal to velocity at point Q. Velocity at point Q. Velocity of fluid particle at point Q equal to Vx plus, you know that at this point velocity is Vx. So velocity is function of y. So what will be velocity at Q? So velocity at Q equal to Vx plus dv over dy into del y, because we are moving del y upwards. So this is a differential. Velocity is a differential function of the distance y. Del v over del y, it is increasing with respect to y. Del v over del y, and total increase in velocity equal to multiplied by del y, that is velocity at point Q. So what will be, suppose in del t point reaches here, this point reaches here, this is new point, we say this is a new point, this is a point Q, this is a point Q will reach at this point Q to Q dash, and this point here reaching P dash, P reaching P dash, and Q reaching Q dash. So this is a deformation of upper layer point, and this is deformation. So this is a gamma. This is equivalent to gamma. This is a strain that is developed. Q dash upon P dash Q. That is a gamma. So we have to find out gamma. What is a gamma? So gamma means strain developed, because in del t time P reaches P dash and Q reaches from Q dash. This is a condition that actually there is no any variation in velocity. Then Q will be at this point, but Q is reaching at Q dash. So we have to find out Q dash Q dash. We have to find out. So how can you define Q dash P Q and Q dash minus P dash? That is equal to Q dash. So we find strain here. How we can find strain here? Strain here we can define by Q dash minus Q upon P dash Q. That is a strain, and we know that Q dash equal to this distance that we will reach Q to Q dash equal to, sorry, that is not a case. Gamma strain we define. Gamma means strain that is developing. Strain means Q dash. That is equal to Q dash Q upon P dash Q. That is equal to Q dash minus Q. सपोज इसको हम लेते हैं, डिफरेंट लेते हैं, Q dash and Q double dash. Q double dash minus Q and Q dash upon P dash Q dash. That is a strain, this angular strain that we want to find. Because you know that gamma equal to approximately tan theta. Tan theta, if theta is very very small, then tan theta equal to theta. That is a gamma. It's strain that we want to develop. We want to find strain. So let us here we see that what is the value of V, that is strain. So Q dash equal to, so gamma equal to Q dash, distance travel in del t time. Distance travel. Here we know velocity is Vx plus del V, dv over del y into del y. Distance traveled into del t time, del t minus Vx del t upon del y. This is a strain. Tan theta equal to gamma. Theta is very small, so we can write a theta. That is a, you can say tan gamma. Suppose you can say tan gamma. Tan theta equal to tan gamma. Better you can take tan gamma. Tan gamma equal to tan theta equal to theta equal to gamma. And this gamma means a strain. That strain can be defined as Q dash, that is equal to Q dash double dash minus Q dash. So here that is if you balance it, you will find Vx, you multiply and solve this question. Simplify this one. So simplifying this one, you get Vx del t plus del v over del y dy del y del t minus Vx del t upon del y. So this term will be removed and this one will be removed. So gamma equal to del dv over del y into del t. This is a strain that is caused due to particle moving q from q to q dash, and because here velocity remains constant at this point vx, so p will reach to p dash. So if strain here caused due to motion of upper particle more compared to lower particle, so this angular deformation takes place. That is tan gamma, and tan gamma this one is very very small, so you can write tan gamma equal to gamma, and gamma is strain that is equal to q dash q double dash upon q p dash q dash, and p dash q dash equal to del y, and q dash we have find out. So this is a strain. And what is the rate of deformation? Means the strain occurring per unit time. So rate of deformation that we want to define means rate of strain gamma upon del t equal to divided by del t. So dv over dy. This is the rate of deformation. And this rate of deformation, you see that this rate of deformation is function of directly proportional to shear stress applied. And what is shear stress tau? Suppose here we applied force F, due to which this plate is moving and surface area of this plate is A. So shear stress tau equal to force upon area, and this shear stress that is developed due to intermolecular attraction forces and the collision of molecule between two layers, and this property is due to viscosity. So this shear stress that is developed due to viscosity is proportional to rate of strain. Rate of deformation, higher the rate of deformation, higher will be applied stress. So tau is proportional to, shear stress is proportional to dv over dy. This is the rate of strain. Removing proportionality constant, or tau equal to mu dv over dy. So this is, you see that higher the viscosity of the fluid, higher will be the applied stresses tau, higher will be the rate of deformation, higher will be the stresses that will develop inside the fluid. So both will reach at equilibrium at higher state of the strain, but it will never stop. Means when we apply force on the plate, it will continue to move over the surface and with a constant rate of deformation. Once you increase stress, again rate of deformation will increase, but never stop. This deformation will never stop. That is a difference between fluid and the solid. So you know that rate of deformation or shear stress is proportional to viscosity. Higher the viscosity, higher force is required to develop motion between two layers. Higher the rate of deformation, higher the stress. So this is any fluid that will follow this condition is known as a Newtonian fluid. Here you can see mu is a viscosity coefficient, and mu can be defined as mu equal to tau upon dv over dy. So here means tau means force per unit area, and meter per second upon meter. So simplify, you will get Pascal second. Unit of the viscosity is Pascal second. And generally we define kinematic viscosity. So kinematic viscosity defined as nu kinematic viscosity. Kinematic viscosity. Generally it is used for the defining viscosity of the gases. Most of the cases we define term use kinematic viscosity for gases in deriving Grasself number, Prandtl number. Here you see that we use generally kinematic viscosity because fluid gas particle move with very high velocity. So here we use kinematic viscosity, that is a nu, and this is a ratio of mu by rho. So this when you simplify this one, you will get a meter square per second. This is unit of the kinematic viscosity. So all those fluids which follow the law of this equation, all fluids which follow this equation are known as a non-Newtonian fluid, known as Newtonian fluid. So let us see how fluids behave. If we draw a graph between the stress and the rate of deformation, how fluids are behaving. Next, in our next class, we will discuss how we can define the different types of fluid under when we by defining by Newton's law of viscosity, how fluid differ from Newton's law of viscosity and why there are different types of fluid, how these fluid differ. So we will discuss this topic in next class. Thank you very much for watching, and please like and subscribe and share it to your friends. Thank you very much.